Hello viewers, in today's session we are going to discuss another important and conceptual problem from integrals, right? So here in this class we are going to evaluate this integral from minus infinity to infinity e raised to 6 times t dt over 1 plus e raised to 2t raised to power 4, right? So let us start. Now see here, first we'll call this integral I, right? And we are going to solve this integral by method of beta and gamma functions, right? So first of all, we'll use the concept of substitution method. So let us first take or introduce a new variable, say u is equal to e raised to 2 times t. So we'll make this substitution here. U is equal to e raised to 2t. Let us differentiate u with respect to t. So we have du over dt is equal to e raised to 2t, because the derivative of e raised to 2t with respect to t is e raised to 2t, and by chain rule the derivative of 2t is simply 2, right? So e raised to 2 times t is replaced by u, so this is 2u, right? So now we can write dt is equal to du over 2 times u, right? Okay, so now let us change the limits accordingly. So here t varies from minus infinity to infinity, right? So when t tends to minus infinity, which is the lower limit, so then we have to find the value of u. So u tends to e raised to 2 times t, and t tends to minus infinity, so u tends to e raised to minus infinity, right? And e raised to minus infinity tends to 1 over e raised to infinity, and this is 1 over infinity, that is tending towards 0, right? So when t tends to minus infinity, then u tends to 0, and similar is the case with infinity, that is when t tends to infinity, u tends to e raised to infinity, and e raised to infinite tends to infinite, right? So our limits are now u is equal to 0 and u is equal to infinity, right? So now let us write this integral in terms of u. So I is now equal to integral from 0 to infinity e raised to 6 times t can be written as e raised to 2t, and here we can take the power 3, right? By rules of exponents, this is 3 times 2 6, so e raised to 2t is u, so we have u cube, right? So here we have u cube, and then for dt we can write du over 2 times of u, and in the denominator we have 1 plus u raised to 4. So now let us simplify it further. We can take half outside the integral. We have 0 to infinity, and here this u get cancelled, and we are left with only u square, and in the denominator we have 1 plus u raised to 4, right? And here we have du. So now we have converted, or we have reduced this integral into this form by making this substitution, u is equal to e raised to 2t, and now we'll express this integral in terms of beta function, right? Because see, the beta function is defined as beta m comma n is given by the integral 0 to infinity, and if we have the variable say x, then we have x raised to m minus 1, and here we have 1 plus x raised to m plus n, right? Where m and n both are greater than 0. So now here we have the integral in terms of u. So we can now compare these two integrals, right? So here we have x raised to m minus 1. Here we have the variable u. So we can form two equations here in m and n. So m minus 1 can be equated to 2, and m plus n can be taken as 4, right? So that we can find out the values of m and n. So m minus 1 is equal to 2. So we have m is equal to 2 plus 1, that is 3. And taking m is equal to 3 in this equation, we have 3 plus n equal to 4. So n is 4 minus 3, that is 1, right? So the value of n is 1 and m is 3. So now we can write this integral as 0 to infinity, and u square can be written as m minus 1. M is 3, so we have 3 minus 1, and here we have 1 plus u raised to 4, and 4 can be written as m plus n. M is 3, n is 1, so here we have 3 plus 1, right? So now this integral can be written as half, and this form is now equal to beta of m comma n, and m is 3. Here we have 2. So here we have beta function, that is beta m comma n. M is 3, n is equal to 1, right? So now we have to find the value of this beta function, right? So to find out the value of this beta function, we can express, or we can use a relation connecting the beta function with gamma function, and the relation goes like this: beta m comma n is gamma m, then we have gamma n and gamma of m plus n, right? So here we have half. Beta 3 comma 1 is given by gamma of 3, then we have gamma of 1, and here we have gamma of 3 plus 1, right? So this is half, and here we have gamma of 3, gamma of 1, and in the denominator we have gamma of 4, right? So now we can use this important relation, that is gamma n plus 1 is given by n factorial. So here we have half, gamma of 3 is 2 factorial, gamma of 1 is simply 1, or here we can write gamma of 4 as 3 factorial. So now we have half, 2 factorial is simply 2, and this is 1, and 3 factorial is 6, right? So 2 and 2 get cancelled, so here we have 1 over 6. So the value of this integral I is given by 1 over 6, right? So this is how, by making use of this important substitution and using the concept of beta and gamma functions, we can evaluate these kind of integrals.